Hello, YouTube individuals. Here we are in the quarantine, and I'm coming at you with a tutorial with all the info you need to know about trig functions evaluating trig functions. Okay, so make sure that you have done the first week's unit and you are comfortable with all of the prerequisite skills. These include converting from radians to degrees. You got to know that stuff. And SOHCAHTOA and those special ratios. That's the important stuff. Okay, so what is going to be new about trig this year? And that will be, I'll start us off. We're talking about what does trig mean when the angles that you plug into a trig function are above 90. Obviously, in the context of SOHCAHTOA, having an angle above 90 doesn't make sense because you can only have 180 degrees in a triangle and one of them's already a right angle. So that doesn't make sense. So first I'll say, okay, why are we going to do this? And this isn't really going to connect till much later till we get comfortable with doing these problems. But like, why are we doing this? I'll just tell you the why for now. The why is we're going to be able to model real-world processes here that are cyclical in nature. Model real-world cycles. So anything, like the temperature of the year, any natural processes that are on a cycle. Trig, sine, cosine, tangent, is actually how you can model that stuff. Okay, so let's talk about, okay, that sounds good, but how? How the heck are you going to do that? How do you have an angle above 90? And the answer is on a circle. The answer is on a circle. And specifically here, we're talking about the unit circle. So what the heck is that? Here we are, a circle with radius 1. And so how can you have an angle above 90? Well, in a triangle you can't, but on a circle you can. Look, here, if we start here as our starting point, and as a great circle, by the way, beautiful circle, and we spin, we're at 90. We're at 180. We're at 270, also known as 3 pi over 2. Do you know the radians? We're back to 360. Oh, what about let's go up to 450? Oh, let's go to 540. You can keep going. So you can keep spinning around the circle. How does the circle work for us here? Okay, say we have an angle. I'm just going to say something simple, like 60 degrees. Let me rotate from here to here, 60 degrees of the arc measure of the circle. Okay, how does this relate to sine, cosine, tangent? Because after we start here and here we rotate 60 of the 90 degrees in quadrant 1, we can draw a radius of the unit circle, and boom, guess what? Now we have an actual right triangle. So you can have angles bigger than 90 because you can just spin around the unit circle, even if your angle is, 5,000 degrees, and you can eventually stop and just make a right triangle. So you can see now how it relates to SOHCAHTOA, sine, cosine, tangent. Okay, now so there's something very special about this unit circle, and that's this axis here, this horizontal one. We're not going to call it the x-axis, we're going to call it the cos axis. And this one up here, we're not going to call it the y-axis, we're going to call it the sine axis. Why is this? Well, let's go back to SOHCAHTOA. Okay, in SOHCAHTOA, so if we were looking at this triangle right here and say, I'm just going to, rather than 60, I'm just going to call this theta, like an unknown angle. If you're looking at that right triangle, and we know that the circle has a radius of 1, you say, okay, let's find the cos of this angle. Okay, so the cos of this angle, we don't know it, so I'll call it theta. This is like x, but you use it for angles. And we know that's adjacent over hypotenuse. So the adjacent is this distance from here to here. Well, what do you call a distance that goes left to right on a coordinate plane? You call it the x distance. This point right here, we could just say we don't know what its coordinates are. It's just some x, comma, y. You know, it's in quadrant 1. We know they're numbers between 0 and 1. We don't know what they are. So if this x coordinate is x, then this distance here is x. So SOHCAHTOA, adjacent over hypotenuse, becomes x over 1, or simply x. Doing this process with sine, we know sine is opposite over hypotenuse. Well, the opposite, that's this length right here. It's the vertical distance to the point. We can call that just y, the y coordinate. So this is y over 1, also known as y. So if your hypotenuse is 1, the cos of this angle is basically the same thing as the x-coordinate of the point, and the sine of the angle is basically the y-coordinate of the point. You say, does tangent fit in? Yeah, it does, because we know, and maybe we haven't gone over this, but tangent equals sine divided by cos. That's a trig identity. If you divide sine by cos, it equals tangent. If you divide SOHCAHTOA, so if you do opposite over hypotenuse divided by adjacent over hypotenuse, and you have that complex fraction, it simplifies to opposite over adjacent, and that's tangent. Now, we already said sine is y and cos is x. So it's basically y over x. Do we have anything else that's the same as the y over the x? Maybe the rise over the run? Yeah, we do. That's slope. So the slope of that hypotenuse, that's the same as the tangent value. Okay, so we have this new picture here. It's the unit circle. You can spin around it and have angles bigger than 90. And we see this special relationship. Sine, cos, and tangent are all represented on this picture. Okay, so we'll start off with doing problems where they give you an angle and they ask for the output of the trig ratio. And we'll start with ones where the angle, maybe we'll just say here, sine of 90 degrees. The angle will be always divisible by 90. Okay, if we use our unit circle picture here, if I start here on the x-axis at the point 1, 0, and we rotate 90 degrees, we end right here. So if this is our starting point, 1, 0, we rotate 90. This point, we know its coordinates. It's 0, 1. Earlier, we said that the sine is the y value of your terminal point, and the y value, the y coordinate of this point right here is 1. So boom. Sine is 1. That was actually kind of easy. Let's do another one real fast. And on these videos, if I go fast, you know, just rewind them, listen to it again. That's the beauty of it. Let's say cos of, I'll go crazy here, negative pi. Okay, it's radians. So you have to know pi is half a spin. It's the same as 180. And I made it negative. What does it mean for us if the angle is negative here? We simply have a way to address that. It just means we rotate in the opposite direction. So rather than rotating up or counterclockwise, if you have a negative angle, you rotate down or just normal clockwise. And if we do that, pi radians, also known as 180 degrees, we end right here. That point, we know it as the coordinates of negative 1, 0. Cos is the x-coordinate of your point, and that's negative 1 here. So boom, negative 1. So if you have angles divisible by 90, just draw the dot on the unit circle, write out what that point is, and just take the sine or cos, depending if it's the x or y coordinate. Okay, now what about angles that aren't divisible by 90? Instead, they're divisible by 30, 60, or 45. Okay, we'll start off with one of these. I'll say sine of, we'll say 120 degrees. So last year that would make no sense because it's in a right triangle. But now we have a way to help it make sense. Okay? Slightly better circle here. I can start at the starting point. I can rotate 120 degrees around this circle is 360 degrees, and it puts me right about here. Boop. Now I can draw the radius of the circle, aka the hypotenuse of a right triangle, and I can make that right triangle. Now we're asked for sine. So the problem now is that we don't exactly know the y-coordinate of this point. We could estimate it, because if the y-coordinate of this one right here is positive 1, just by looking at it, it's like, I don't know, 0.75? Something, I don't know. Sure, we can estimate it, but how can we do it exactly? Okay, I have some steps for us here, steps of a process, and we've already done some of them, so I'm just going to show them to you. I've already written them down. These are the steps to evaluate, so let's go through them. Specifically, if you got an angle divisible by 30, 60, or 45, also known as something divisible by pi over 6, pi over 3, pi over 4, the radians versions of 30, 60, and 45. How do you know if it's in radians? Just look at the denominator. If it has a denominator of 6, 3, or 4, it's divisible. Okay, so what's this process here? If we're going to exactly find the sine or cos value or even the tan value, we're not going to estimate it. Step 1, you need to do what we did and draw the terminal point of the angle. Rotate, starting from the point 1, 0, rotate up counterclockwise, however many degrees it says. Here my hint to do this accurately is pizza pieces. Why? Because chopping a circle into pizza pieces, aka sectors, is kind of an easy way to do it. You know, if you chop a circle into 45-degree slices, that's 8 pieces in a pizza. What about 30 degree? That's 12 pieces in a pizza. In 60 degrees, there are 6 60-degree slices and 360. So kind of thinking about it like that makes it easier to quickly go around your circle and do it accurately. And you'll see me do it there in a second. Okay, so you draw that just dot. You rotate and draw the dot. Then what? Make a right triangle. Okay, how? As we showed a second ago, you want to draw a radius that makes the hypotenuse. And here's the key thing. You want the triangle to have a leg on the x-axis. Exclamation, exclamation, exclamation. I emphasize this because this is just a common thing I see students do wrong. When they go to their dot on the unit circle, they draw a horizontal segment to the y-axis, and then you have a right triangle with one of its legs on the y-axis. No, no, no. Every time you do this, you draw a vertical segment and it connects to the x-axis. Okay, what next? Now you go into your triangle. You label the central angle in the little right triangle. Figure out what it is, the one that touches the origin. And from there, you're either going to have a 30, 60, 90 or a 45, 45, 90. And thus, you know those special ratios. You can fill those things in and finish the problem with SOHCAHTOA. So you can flip back to this if you need to, but let's just try to do that now. Okay, here's the one we've done. All right, we started, we drew our dot. You know, this was like divisible by 60. So I imagined a circle that was really cut into 6 pieces, as we see here. And I just go 1, 2. I'm at the 120, and so that's kind of why I knew to draw the dot there. Okay, notice we drew a vertical segment down. So now we have a right triangle here that has one leg on the x-axis. If we were to draw this horizontal segment here, we'd be doing it incorrectly. So we now have a right triangle. Its central angle is right here. And if we rotated 120 degrees to get to this point, how much is left over for half the circle? 60 is left over. So that there is a 30, 60, 90. You can put in the 30 if you want. Right triangle. I'll try to draw these bigger so you can see them. Now that we have a 30, 60, 90, we know its ratios. The small leg of a 30, 60, 90 is 1. The long leg is root 3, and the hypotenuse is 2. Now you might say, wait a minute. I thought you said that this segment here is on the unit circle, it's a length of 1. Okay, you're right, it is. But we put these numbers in here to just represent the ratios. So this is not equal to 2. This segment vertical here does not equal to root 3. We just list these in as ratios, numbers, because we're about to take a ratio, and then it doesn't matter that it's not 1. Okay, so understand, we're just doing this here to make a ratio. Now, if you noticed on step 4 of this list, I said, when you fill in the ratios, if you ever go left or down, it counts as negative. Take a look over here. You know, this vertical segment is up into quadrant 2, but this horizontal segment, it went to the left, so this has to be labeled as -1. So when you fill in these ratios, the 30, 60, 90, or the 45, 45, 90, you already know these things. You got to put them as negative if you go to the left or if you go down. So if a right triangle is in quadrant 3, both that vertical and horizontal would be negative. The hypotenuse is always positive. I'll say it again. The hypotenuse is always positive, so you don't have to worry about that. Okay, so we've made our triangle. We put the ratios in. Now the easy part, SOHCAHTOA. This is sine. That's opposite over hypotenuse. Look in this right triangle here. From the central angle, what's the opposite? Root 3. What's the hypotenuse? 2. Boom. There you have it. Root 3 over 2. Very, very easy. Okay, let's do another one real quick. I'll say, draw bigger this time. I'll say, let's go, sure, tangent of, I'll go crazy, -7 pi over 6. Okay, now notice, what is our angle divisible by? It's pi over 6. Draw a bigger circle here. Oh boy. It's pi over 6, that's like 30, so this is 1 divisible by 30. That means if you chop the 360, chop the pizza up, you would have 12 pieces. There's your 12-piece pizza right there. Okay, so starting at this point and rotating down because it's negative, how do I do -7 pi over 6? I go 1, 2, 3, 4, 5, 6. Boom, 7. That's our terminal angle. You also, you could convert it to degrees. This would convert to -210 degrees. And then you could just think about it in terms of degrees if that makes it easier. But we've made our point. What next? We draw a vertical segment touching the x-axis. And now we got our right triangle that you can kind of see there. There's a lot going on, so I'll draw the little lines. I'll shade it a bit. This triangle right there. Now, our central angle here, since this is pi over 6, there's a 6 in the denominator. I know that this is a 30 as the central angle. Now I can fill in the ratios. It's another 30, 60, 90. The little leg is going to be 1. The hypotenuse is 2. And the long leg is root 3. And once again, we're in quadrant 2. So that's a -root 3. SOHCAHTOA, opposite over adjacent. Looking at our triangle, the opposite of the 30 is 1. The adjacent is -root 3. There's your answer. Now, unfortunately, this answer is not simplified. Our rule is no square roots in the denominator, so we have to multiply by root 3 over root 3, changing the fraction to -root 3 over 3. They call this rationalizing the denominator. I don't know why they made this rule, why they said no radicals in the denominator. It certainly makes it easier to like add fractions now that you have a whole number down there and not a irrational number. But notice multiplying by 1 in this form is how we take care of that. Okay. What else we got? We got some more stuff. We're almost done here, odds and ends. What if you have a ratio that is secant, cosecant, or cotangent? You might never have seen these, but we call these the reciprocal ratios. And actually, they're not that hard. Maybe you've just seen them as buttons on the calculator. What do they mean? They mean these are just reciprocals of the ratios we already know. So sec is the same thing as 1 over cos. Oops. Cosecant is 1 over sine. And cotangent is 1 over tangent. Don't confuse this with the inverse function on your calculator, where you plug in a ratio and it gives you the angle. This isn't the inverse, this is the reciprocal. That means 1 over something. So if you know a cos, the cos of some angle is 7. What's the sec? 1 over 7. You just put it in there and make that. And they're just a little weird because the one that starts with S goes to the one that starts with C. And the one that starts with C goes to S over there. So how could we do one of our problems here? What have we not done? Cos. So let's say cos of, or not cos, we got to pick one of these things. So let's say secant of maybe 7 pi over 4. So there's our problem. Secant, 7 pi over 4. Okay. We're pretty much not going to address this secant business till the very end. So let's take a look. We're going to do the same steps that we just did. Step 1, we need to label our angle. We need to rotate. Start here and rotate 7 pi over 4. Now to me, I see this as an 8-piece pizza. So we're just going to go to the 7th piece. 1, 2, 3, 4, 5, 6, 7. Boom, there we are. You also could convert this to degrees, and this would be 315 degrees. Okay, now we're going to draw a vertical segment, and thus make a right triangle that has a leg on the x-axis. Don't make a horizontal segment here. Now, we need to label the central angle. Since we have a pi over 4, we have a 4 in the denominator. That shows me it's going to be 45 degrees. It kind of looks like a 45 degrees. If you draw your unit circle accurately, the right triangle will naturally have the right shape. This looks like a 45, 45, 90, and it'll look like a 30, 60, 90 if you label the angle correctly. Okay, so now we have those ratios for 30, 60, 90. The legs are 1, and the hypotenuse is root 2. Will either of these be negative? Well, for the horizontal leg, we went to the right from the origin. That's positive. But for the vertical leg, we went down. So that one will indeed be negative. What about the hypotenuse? Always positive. And so there it is. Now all we have to do is SOHCAHTOA. Wait a minute. This isn't sine, it's sec. So if these are the reciprocals of SOHCAHTOA, you just flip SOHCAHTOA. So if this is 1 over cos, if that's adjacent over hypotenuse, now we have hypotenuse over adjacent, hypotenuse over opposite, and TOA will flip to adjacent over opposite. So for secant, cosecant, and cotangent, it's not really SOHCAHTOA, it's more SHA-CHO-TAO. SHA-CHO-TAO. There you go. So since we have secant over here, that's hypotenuse over adjacent. Let's look at this thing. Hypotenuse is root 2. And the adjacent, that's the one touching the angle, that's 1. So root 2 over 1, also known as just root 2. Okay. Finally, what if you see an angle that's not divisible by 90, 30, 60, or 45? So I'm just going to pick one up. We're just going to say whatever. Sine of 35 degrees. What about cos of pi over 5? We didn't do that one. What about sine of just 0.8? And you might say, what the heck is that? Well, is there a degree symbol? No, so this is 0.8 radians. Remember, we write the pi, but pi is around 3. So this is an angle. If you don't see the degree sign, it's an angle. So how would you do all of these? Well, you could estimate it using our method. As in, I could just draw a 35-degree angle, draw that point, and then estimate the x and y coordinate to kind of get a good estimate. If you want the exact value for all of these, it has a simple solution, and it is your favorite thing in the world. It is the calculator. This is now a calculator-only problem. We can't do it on our own. It's pretty easy. You just plug the angle into your calculator with the function, hit enter, and boom, there you go. Now, the calculator will give you a decimal. It won't give you a nice exact answer with the square root in it. Like, it won't say root 2. It'll say the decimal approximation of that. So you have to round it after 3 significant figures. But it's pretty simple there. Now, if you might say, how do I do radians on my calculator? Well, on a TI-84, if you hit the button that says mode, then you see you can switch it from radians or degrees mode. And even if you're using a simpler calculator, like the TI-30s, there's a button at the top that says DRG DERG. You hit that, and then it'll say switching to radians. Or on your phone, you can even turn the thing sideways, and there's a button that switches it to radians. Okay? So that's all of the ideas here on evaluating trig functions. Evaluating means when they give you the angle and they want the ratio. What's new about this? Well, now we're dealing with, taking a look at the problems we just did, angles that are bigger than 90 degrees. How does that even make sense? You can throw them on that unit circle, and we have these steps to help you create a right triangle on that unit circle, label the ratios you already know, and just finish these things with SOHCAHTOA. That's all I got. You know, you can play back some of these examples and work through them again. Go ahead, and you can also peruse some other people's YouTube videos if you want, but I'll warn you, a lot of people have procedures, a lot of teachers teach this in a really crappy way, I'd like to say, where they do like a little trick where you don't understand what's going on. This way, it's a little bit longer, but it's based on things you already know how to do. You already know how to rotate around a 360-degree circle. You already know about the special ratios. You already know SOHCAHTOA. So this way it makes complete sense. Okay, so check it out and try some problems. Good luck. This stuff will be extremely important next year in ACE, Pre-Cal, and IGSY 4. Peace!